no need to have mic. So I'm glad to introduce the second lecture by Diletta Olliaro. And Diletta is finishing her PhD under the supervision of Andrea, who just talked. And today, she also in Venice. And you see the fantastic picture of the, I wish we have the same type of quality for the representation of our universities. And so Diletta will today discuss multi-party gaming on the edge, please. Does it work? Yeah, it works? Okay, so, but I think this works, right? So
yeah, that works. Okay. Good afternoon, everyone. And first of all, thank you for having me today. As Professor Bacheli just said, I'm going to talk about multi-party gaming on the edge and related the performance issues of distributed online gaming. So let me start by saying that during the pandemic, we witnessed some few years ago, the gaming market increased by 25% and reached like a quarter of $1 trillion, and is expected to keep increasing yearly and reach like $500 billion by 2030. So these are kind of huge numbers. The fact is that people nowadays is constantly trying to play from their mobile devices. And that is why there is a huge interest on this market from the perspective of network providers. So, of course, this kind of infrastructures bring some challenges. For example, what should we do in the network from a perspective of quality of service and quality of experience? And how do we handle multi-party interaction with many, many users? This becomes a scientific problem in which we need tools to design and evaluate and ask ourselves how can become online gaming viable to everyone that has fast access to the internet, at least. So our contribution in this field started by trying to give an architectural design from which we proposed an analytical model, which we used to give a performance evaluation study. This work was actually presented in IFIP Network in 2024 and is a joint work with Professor Vincenzo Mancuso and Professor Marco Aimone Marsan from Indea Networks, and Paolo Castagno and Professor Matteo Sereno from University of Turin. So let's talk a second about the past. As many of us know, gaming started with the large hardware that required huge processors and engines for handling the graphics behind games. And in the past, we didn't have the thing of having like interaction over the network and being able to communicate with other gamers around the world. Nowadays, gamers want to play anytime and anywhere. This is why what happened is that games started to be viewed as a virtual network functions, following the gaming as a service paradigm. Okay. So what happens nowadays is that players transmit game commands, usually to a network infrastructures, which can be the cloud, for example, where the virtual network functions collect these commands, amalgamates them, and then encode them and send them back to the user. So what happens is that the user facility, let's say, just need to being able to send the commands over the network, and the feedback for the quality is receiving from the network itself. So the main problem in this kind of framework is that only players with broadband access and low latency are able to properly experience online gaming. This is because in order to have the gamers' actions embedded in your videos, the gamers with whom you're playing, embedded in your video streaming fast, you need consistency over the network, and you would want to have like real-time interactions. Otherwise, of course, your quality of experience will decrease a lot. So these kind of requirements led the International Telecommunication Union to produce some recommendations to predict, plan, and manage online gaming quality of experience. Some related work to this topic. Actually, there are not very much, and the majority of them lack analytical insights. Especially from a gamer, from the game provider perspective. And what was very valuable for our study was that there were some investigations and measurement studies about the main network characteristics influencing the quality of service and experience in this context. And these measurements were the actual parameters and you will see it later, that we used for our analytical model and to perform our performance evaluation study. So what's actually new in our work? We propose the first, at the best of our knowledge, stochastic model for the evaluation of the success probability of a multi-party game. So what we envision is a new fully distributed edge gaming architectures, thought on as network slice, and in which game is provided through virtual network functions and following the gaming as a service paradigm. So what is kind of new in the architecture we thought of is that both game control and video rendering are brought to the edge instead of being divided between edge and cloud, or being only in the cloud, which means that we bring the computing facility closer to the user, minimizing latency. At the same time, we have the issue of less capacity with respect to a cloud, less computing capacity with respect to a cloud infrastructure. So our model kind of it builds upon one of the latest ITU recommendations, except for the fact that we propose this probabilistic approach that was not embedded in that recommendation to evaluate the quality, to estimate the quality of service.
I have a question, sorry.
Yes.
If you put everything at the edge, for me it's not clear how you can play network in network gaming with people that are far away. Do you consider this kind of game?
We consider geographically distributed gamers, not like for the moment, not that much. Okay. What could happen is to have some kind of smaller cluster with edges so that you can play not locally, but in a restricted area, and then eventually have less cloud infrastructure to interact with to go globally. Okay.
Okay.
Yes.
You mentioned, of course, that you have a stochastic model. What is stochastic here? The number of users at a certain time, the behavior of the users?
No, the model itself, because we are going to use queues to describe the latencies in the network, and so this embeds in the stochastic thing in the model.
Okay, but the number of users is also evolving stochastically?
No, the number of users is given as a parameter and is usually fixed, like fixed or yeah.
And the behavior of the users is not influencing the traffic in your model?
The behavior of the users, as we use this measurement study to have parameters for our model, what we did is to assume of having as parameter the approximate traffic every user produces to its infrastructure and then to the edge infrastructure itself.
Thank you.
Thank you. Okay, of course, this proposal of ours comes with some challenges. As I kind of anticipated before, of course, the edge has the advantages of reducing latency. However, at the same time, what happens is that you need to manage the allocation of the players on these edge facilities. And which is not that easy because you need to take into account the load, the capacity of the edge facilities themselves, if they have a buffer, for example. And the other thing is that, as I was saying before, you need to ensure consistency. And in order to do so, you need to have gamers' comments to be embedded into their own game and the other players' video streaming inside a certain timeout with a certain probability and with a reasonable packet loss threshold. So this is the kind of architecture we thought of. We have edge servers that are deployed as virtual network functions accessible via user plane functions. And what happens is that the edges receive players' commands and modifying the rendering for all the interacting players. So what we need, we gain here, again, is low latency, reduced network resource utilization. However, we need to manage these virtual network functions interaction and assure to have a certain success probability to be able to ensure to the final user a certain quality of experience. So our probabilistic approach consists in having a queuing model. So assuming to have 4 main delay components in this kind of framework, we have some fixed delays due to geographical distribution of the various components of the network. And then we have some random component in user access to transmission, some like noise, retransmission because of packet loss, or for example, oscillation in the network and so on and so forth. Then we have, of course, the variable queuing and processing time at each component. And finally, we have a fixed delay for video adaptation when going in downlink. And this was set in all the experiments we are going to see in a short time to 10 milliseconds. So assuming that we can consider all these delay components to be independent, and assuming that we can model everything with queues, what we have is that we are able to compute convolution of the distribution of the sojourn time, so that we are able to consider if we have if we are respecting a certain threshold. Yes.
Go back to the
yes.
So I'm trying to figure out so what is the game streamer exactly here? So
that's our so we have the edge facilities, and that what happens is that we need to adapt, we need to embed in the game the actions, and that would be when we go back, like the part of the video streaming that is transmitting back the game with the commands embedded.
Okay, so this is one edge, right?
Yes, one edge.
And so you interact with the other players with the other edges.
Yes, exactly. Yeah, maybe I should specify this. We are taking into account multiple components. So these are the delays that each user is facing when interacting with a particular edge, and then we have to also consider them from the other side, because we also need to go to the other players, which may be connected either to the same edge I am or to another one. And we incur in the same delay components.
But so, for instance, if the game requires interaction with somebody who is on edge 2, the delay will not be the loop that you mentioned, the blue plus red. You will have to go far away to interact with the actions of edge 2 players, and there will be an interaction back to this edge, which will go to the red.
So the convolution of delays we are considering is from myself to my edge, and come back, because I need to also embed in my own game my actions, and then from myself to my edge and to the other edge I need to communicate with. And this will give the delays components that are going to influence the probability of success we are going to talk in a second. Yeah.
So I don't understand, but I'm not. I mean, so if in H2 there is a player with whom I'm playing, I play chess, right?
Sure.
So, I have to go up to H2, and the end-to-end delay will feature things that take place perhaps locally, but also things that take place very far away. And the delay of the actions will involve something which has a loop which is much bigger than this one, right? Is it, perhaps I'm mistaken, right?
No, yes. If I understood correctly, I think that's it. I need to go up to edge 2.
Yeah.
But then I do not need to consider also, I need to arrive to edge 2 and be able to embed my actions inside a certain timeout. But I don't need to consider also the feedback I'm getting back after that.
Okay.
I think that what comes to me from edge 2 is this branch on the left. This one that is labeled from other edge virtual network functions, right? So I just need to measure the delay between the moment I decide to move my tower and the moment I see the tower moving.
Okay,
yes.
and I move my tower, but also you want to see what happens for the player at H2.
This command over there, and over there they will take it as an input whenever it arrives, but you won't be.
Okay.
Yes, like following this example, I need the delay of seeing my own tower moving and the other player seeing my tower moving.
Okay. Thank you.
Sorry. Okay. So, of course, we have some simplification and assumption. First of all, we assume that within the gaming slice, each base station hosts a single player, and that each user playing function serves a single base station. But this is actually coherent with the extreme 5G densification process. And then we need the stationary assumptions to assume that the intensity of stream does not change over time, so that we are able to consider also cases in which we have traffic peaks. And finally, we assume that players are not aware of the location of all gamer virtual network functions to be notified, while the actual edges facilities, of course, are. And this is coherent with high-speed networks such as optical rings. So we give here some key definitions. We will need the definition of self and cross latency, which is exactly what we were mentioning now. So self latency is the time I need to see my own commands and game actions embedded in my own video stream, whereas cross latency is the time I need to see my own, is the gamers I'm playing with the time they need to see my own game actions and comments in their video stream. And what we have is that we consider scenarios. Scenarios are actually tuples describing the gamer allocation in the edges. So, for example, if I have 3 edges in my network and 3 customers and 3 users, I can place these users in different combination in these edges. And of course, they will incur some kind of different delays. For example, if I have scenario 1 to 3, this would be player 1 connected to edge 1, player 2 connected to edge 2, and player 3 connected to edge 3. So we perform a queuing analysis, taking into account losses, because we are going to model edge facilities as MMNK queues. And we are going, what we did was computing the Laplace transform of sojourn times of these individual queues to embed the delay components. And we obtained the overall delay. and check that this is under a certain timeout threshold. This is actually what this is actually our definition of success probability. So game commands delivered to the edge servers where my fellow gamers are connected to, and we have self and cross latencies to be lower than these timeouts, so that this would be the single player success probability. And in order to have the multi-party game success probability, we multiply each single player success probability. Okay, so let us play a bit by showing our...
Just a question.
Yes.
How to say? You say that so we calculate some probabilities of timeout. What happens when there is a timeout? Is it just a freezing of the game, or is it something that the player cannot play again?
No, it's like okay. So for the it's again the kind of recommendation and measurement studies we were talking about. In order to have an immersive gaming experience, you would want these kind of timeouts, considering the self and cross latency, to be around 100 milliseconds, but that's actually already a lot. So that's our timeout. And in case we are not able to satisfy it, our success probability will drop.
Okay. But in practice, the gamer can play a still play, but with some degraded condition.
Okay, can play, but it will see. No, can play, but it would see it like when you see the like when you're looking at Netflix and there is the buffering and you have problems of actual real time experience. So yeah. Okay, so we are going to show now our performance analysis. We have some application requirements, again, from the related studies we were mentioning before. So unless differently specified in these few first experiments, we are going to consider 2 edges and 2 players, and the various combination that we can have in this case. Edge 1 is equipped with 5 processor, edge 2 with 10. Each processor is able to serve 1,000 packets per second. And the edges, as I already said, are modeled with MMNK queues, where we consider the case of infinite buffer, no buffer, 2 times the system capacity as buffer, and 4 times as the system capacity as buffer positions. And then we also consider the MD1PS queue case to embed the more realistic case in which the edges facilities operates under a round-robin scheduling policy. Then we have that from these studies and their recommendations, we have that in order to have an immersive game experience, we would have 1 megabyte per second in upstream and 5 to 50 megabytes per second in downstream. Packet loss is actually tolerated up to 10–30% in upstream, but that's just because the key performance indices feedback is very redundant. And then we have that instead packet loss is tolerated up to a few percent in downstream. Latency requirements, as we were mentioning now, are around 100 milliseconds, but that's already quite a lot, and that's why we mainly consider the timeouts of 75 milliseconds in our experiments. So the interesting thing here is that we also performed some experiments in the wild, in the actual internet. We set up a flexible set of instrumented microservices where we developed our 3 main blocks: client, server, and user playing function. And of course, we use these kind of infrastructures to collect data and to validate our model. What was quite surprising is that collecting the statistics and producing 90% confidence interval, we obtained quite good results, and we can see them from these arrows here around these lines, these curves that I'm now going to explain. And this was quite surprising because we did some simplification for our model, but they seem to be reasonable, at least from this kind of experiments. So here we show the success probability of each player, S1 being player 1 and S2 being the success probability of player 2. And we have 5 curves for each plot. We consider all the kind of buffers that we were explaining before. And again, we have a timeout that is 75 milliseconds, a user edge delays that is considered to be around 20 milliseconds. And then, of course, if players are connected to different edge facilities, we would also have some inter-edge latency that we need to consider. So as we can see in the case of the MMN and MD1 PS queues, as we reach 1 with the load, delays converges, so our success probability goes to 0. Then what we can appreciate from this kind of plot is that some buffer is very helpful because we would limit the amount of queuing delay incurred by each gamer. At the same time, too much buffer would increase this delay too much, and of course, we would have worse performance in terms of the success probability. What I should mention is that for fairness of comparison, in the case of the MD1 PS queue, we have just 1 server, so we decided to put it like n times faster, because otherwise, of course, it would not perform as well. And what we can see is that that is the case that performs better almost in every experiment. And that is because as far as you have low load, you would have few gamers sharing this huge amount of computing capacity. From the other hand, you avoid, of course, the disadvantages of sampling from the heavy tail from the tail of the exponential distribution. Yes.
So these are results based on this Laplace transform analysis.
Yes.
And you use that to evaluate the tail and the chance that it vibrates.
Yes. So we use the Laplace transform of the sojourn time. We consider actually the cumulative distribution function computed in a point, so that we have the probability of being under that.
So you invert the Laplace transform?
Yes, and I invert the Laplace transform in that numerical point, which is the timeout.
75.
Exactly. And of course, we also consider blocking probability due to the finite capacities, and we multiply everything, and that gives us our success probability.
And the Laplace transform is rigorous because actually with this vision of this internal and external thing, everything is acyclic, right? There are no cycles. Right?
Sorry?
The queuing network is fully acyclic.
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 Yes. 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 Yeah. Okay. Okay. Then we studied the impact of timeout. So here on the epsilon axis, we have the success probability of the whole multi-party game. So the multiplication of success probability of gamer 1 and gamer 2 over a single timeout. Of course, as expected, if players are connected to the same edge, as in this case here, what we see is that we are able to satisfy much lower timeouts with respect to the case in which they are connected to different edges. The other interesting thing here is that we can see how the purple curve and the green one, these two here and these two here, are always the worst. And that's because we are considering, so in the case of the green one, which is always the worst, we are considering the case of no buffer, and that what happens there is that we have a loss probability so high that our success probability for the gamers drops and is not able to reach reasonable success probability thresholds. As reasonable, we mean at least 80%, so not to have the lagging thing we were mentioning before. So here we have one of our, in our opinion, most interesting experiments. What we tried to do was to compare this kind of framework if it was put on a cloud infrastructure compared to as if we put it on an edge infrastructure. So we have that. So we consider different edge scenarios. And these are represented by the solid curves. We imagine to have again 2 gamers. One is connected to edge 1 and has a delay from its edge of 10 milliseconds. The other one is connected to edge 2 and has a delay of 15 milliseconds to its edge. Then we consider inter-edge latencies from 10 to 35 milliseconds. Then we consider the cloud scenario, which is the dotted curve. And here we consider both gamers to be connected to the same cloud facility and to represent, for fairness of representation of this kind of technologies, the cloud would be a bit more far away, but at the same time more powerful. So what we did is that we consider each gamer to be at 30 milliseconds from the cloud. And we have that the cloud facility has double the computing capacity of the edges. So both are considered at 90% load. And what is interesting here is that edge scenarios always perform better than the cloud one, unless the distance between the 2 edges is actually surpassing the distance between the single gamers and the cloud. So this would seem to indicate that distributing players over the edge kind of works. So our model is not limited to the case of 2 edges and 2 gamers. We are able to consider an arbitrary number of edges and gamers. And in order to do so, what we do is to define communication clusters. Communication clusters would be a set of those gamers that are actually actively interacting among themselves. And so in order to show some experiments in these more, let's say, complicated case in which we have to take into account more components, we show some results for a scenario in which we consider 10 gamers connected on 3 different edges, each one with 10 processors. And we decided to have fixed delays composed as follows. So the first 3 gamers we are considering are closer to the first edge. The second 3 gamers we are considering are closer to the second one, and the last 3 are closer to the third edge. So what we consider here are 3 different scenarios. In the first one, this here, okay, timeout is again 75 milliseconds. When we say that the user is connected to his closest edge, we have that he has a 15 millisecond latency between them. When it's the non-closest edge, we have 20 milliseconds of delay, and inter-edge delays are always 20 milliseconds. So the first scenario we consider, we call it the best one, because it's the one in which we consider each gamer connected to its closest edge. And of course, we can see that besides the case with no buffer at all, which we will address in a second, in every other case, we are performing quite good up to certain load values. What we consider here is a scenario in which 2 out of 10 gamers are not connected to the closest edge. And in the last case, we have that 4 out of 10 edges, gamers are not connected to the closest edge. And what we observed from this kind of experiment is that we actually pay a high price from not connecting the users to their natural edge, let's say. Then what we consider here are the different clusters we can consider. So for example, if we have 10 gamers, we can imagine of having 5 of them, the first 5 of them playing among them, and the second 5 playing among them, all the 10 of them. So we see that, as I anticipated before, no waiting line kills bigger cluster totally. And that is because you would have a lot of requests and you would not be able to serve them all without some buffer to wait in. And the other thing that would sounded surprising, at least to us in the beginning, is that these curves drops so fast when considering 10 gamers instead of 5. But that is given by the fact that we need to multiplicate, like in this case that we have 10 gamers, 100 delays, 100 success components, because we need to consider each couple success probability. So from this kind of 3D histograms, we can actually appreciate the cost of allocating edge gamers to their own natural edge or not, but we can also appreciate the influence of the buffer to this kind of scenario. In fact, here we are considering the case in which we have no buffer, and this is our best case, and we can see that we have already a failure probability that is not really 0, and if you multiply it several times, you would obtain the results we've seen before when considering a load 0, 5. And here you can see that when we do not allocate gamers to their closest edge, we have much higher failure probability that are going to influence a lot our success, our overall multi-party game success probability. So wrapping up, we proposed, at the best of our knowledge, the first stochastic model for evaluating edge gaming. We performed an analytical study with model parameters driven by measurements studies on actual networks. We provided also an experimental evaluation with traffic generators and microservices mimicking the edge facilities we talked about. And we think that our major takeaways are the fact that understanding the gamer success probability in multi-party games enables to enhance the gaming experience optimization. We think that distributing players among edges can help a lot the quality of experience of the final users, and that the best allocation strategy can vary. And that is why we think that our model could actually be used by game providers to provide a better experience to final users. And of course, we have in mind some future work for this because we have a lot of fun doing this work. So we aim to analyze more realistic gaming workloads. We aim to study also the impact of varying network conditions, enrich and extend the scenarios that we considered so far. And we would also like to try to investigate, since we have this nice tool, the optimal allocation strategies in order to be able to adapt to dynamic conditions and to provide the best possible quality of experience to the final users. So thank you for your attention.
Questions?
One perhaps to start with. So, I mean, this edge thing is meant for wireless in particular, right? So, and how can one entangle the wireless conditions in these ML models? I mean, so for instance, I mean, the 2 players, or if there are 5 players in this cell, they will interfere with each other on the uplink or the downlink. And so there is a wireless, there are wireless conditions with respect to this local edge. And so how can one take this into account in the model? The Shannon type interaction between users in a given cell?
I think we take that into account by considering the variable. We consider fixed delays and then a variable amount that takes into account fluctuation of the signals and noise and this kind of thing. So I think it's embedded in the model, but maybe I'm wrong. No, I think so.
So maybe in the parameters of the the delays and the. Yeah, so I mean, so if there are many users in a given cell, they will interact negatively with each other. Because their Shannon rate, they will interfere with each other, and their Shannon rate.
Yes, right. Maybe. So, for example, when we considered, I'm sorry, I'm not sure if I quite understood the question, but if I did, I forgot probably to mention here that in this case we are considering only two gamers, but actually the load here is representing another set of users connected to the same edge facilities that are inputting traffic in the network. The difference is that we are not detailing their performance and we are just considering them as background traffic. And we detail instead the performance of the two gamers I presented when talking about, for example, this kind of results. So we consider to have also other interactions and players in the network. We embed them either in the load or by consider their delay components also. I don't know if this answers quite fairly the question.
Yes, background traffic is present.
Okay.
Other questions, comments? Okay, so if not, let's thank.
Okay, thank you so much.